Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and today is March 19th, 2020, and today in the Northern Hemisphere we are celebrating the spring or vernal equinox. Today is the first day of spring, and I thought this would be a great opportunity to talk to you about why we have seasons here on Earth. But before I mention or discuss the scientific reason for seasons, I do want to dispel one common myth about our seasons. And that common myth about our seasons is that our distance to the sun has something to do with the seasons. Here's a diagram that shows us the Earth's orbit around the sun. You probably learned back in school that the Earth's orbit around the sun is an ellipse, which means there is one time of the year when we are closest to the sun and one time of the year when we are farthest from the sun. And that is true, the Earth's orbit is elliptical, but most people in their heads grossly exaggerate the ellipticity or the eccentricity of the Earth's orbit around the sun. The truth is, the orbit is so close to a perfect circle that in this diagram you can't tell that the Earth's orbit isn't perfectly circular. In fact, when we are farthest from the sun, we are 94.5 million miles from the sun, and when we are closest to the sun, we're 91 million miles from the sun, and that means the total change in distance from closest to farthest is a little around 3%. Now, there are a couple things on this diagram that tell us that our seasons do not come from our distance to the sun. And the first one is the time of the year when we are closest and farthest from the sun. So every year in early January, we are closest to the sun, and every year in early July, we are farthest from the sun. This year in 2020, we were closest to the sun on January 5th, and this year we will be farthest from the sun on July 4th. Now look at those dates. January 5th was the coldest time of the year, and yet we were closest to the sun. July 4th, it will be the hottest time of the year, and yet we are farthest from the sun. And this is true every year in the Northern Hemisphere. When it is coldest, we are closest to the sun, and when it is hottest, we are farthest from the sun. That alone tells us that our distance to the sun has little to nothing to do with our seasons. The other thing on this diagram that tells us that the distance to the sun probably has little to do with our seasons are those distances. As I said, when we're at the closest, it's 91.4 million miles. When we're at our farthest, it's 94.5 million miles. That's a difference of 3 million miles, and that sounds like a long distance to you and me, but it's actually really small compared to the average 93 million mile distance to the sun. And let me give you an analogy. Imagine that it's wintertime and you're warming your hands around a campfire, and you hold your hands up 7 feet away from the campfire. That's about 91 inches, a little bit more than 7 feet. Now take your hands and move them to 94 inches from the campfire. You're moving them 3 inches further away. You can imagine that if you're 7 feet from the campfire, your hands will be no warmer at 91 inches than they were at 94 inches. Both of them are essentially the same. They certainly don't account for the difference between a hot summer day and a cold winter day. That distance, that change of 3 million miles cannot explain our seasons on Earth. But the campfire analogy does help us understand a little bit about why we have the seasons, and that is when I'm warming my hands around the campfire, I put my hands like this and not like this. And I don't put my hands edge on to the campfire because if I did, my fingers, my hands would intercept very little of the heat from the campfire. But if I put my hands like this, they will intercept the maximum amount of heat from the campfire. It will make my hands the warmest, and as we'll see, this is why we have seasons on Earth. But to understand that scientific model for the seasons, we'll have to talk about the Earth's rotation. And it's important to know that the Earth does not orbit the sun with its axis straight up and down. The Earth's axis of rotation is tilted by about 23.5 degrees with respect to the Earth's orbit around the sun. That is, the Earth doesn't orbit with its north and south poles straight up and down, but they're tilted by 23.5 degrees over. Now, it's important to know that this tilt remains constant throughout the year. I've often heard people say that the reason we have seasons is the changing tilt of the Earth during the year. But I want to emphasize that that 23.5 degrees is constant. It doesn't get more or less during the course of the year. Not only does it stay constant, but the direction in which the Earth's axis is facing stays constant. That is, the Earth's north pole always points to the same location in space, and that location in space is marked by a moderately bright star called Polaris, the North Star. As the Earth orbits around the sun, though, various hemispheres receive either more or less direct light from the sun because they are either tilted towards or away from the sun. And this diagram will help explain that. This is a little animation that's going to show the Earth orbiting around the sun. Before I start the animation, though, I want you to watch the tilt of the Earth's axis. First of all, you'll notice it's tilted over by about 23.5 degrees. And I want you to notice that that tilt never changes. It never gets tilted by more than 23.5 or less than 23.5. And as the Earth orbits around the sun, I also want you to notice that the orientation of that tilt doesn't change. It always stays oriented in the same way. So let me go ahead and start the animation here and keep an eye out for the tilt. Notice that it doesn't tilt any more or less. And notice that the orientation of the tilt remains constant. But what you will see is that at different times of the year, different hemispheres are facing towards the sun. In December, the southern hemisphere is facing towards the sun, whereas in June, the northern hemisphere is facing towards the sun. This circle that just came up represents the Earth's equator. And there are times of the year when the sun is north of the equator, like it is now, and times of the year when the sun is south of the equator, as it is now. The sun alternates from being north of the equator to crossing the equator to being south of the equator. And that is what causes our seasons. During the course of the year, the sun goes from being north of the celestial equator to being on the equator, to being south of the equator, to being on the equator, to being north of the equator. And it comes about because the Earth is tilted 23.5 degrees over, and that tilt doesn't change as we orbit the sun. So what practical aspect is this in the sky? What does this look like in the sky? So this diagram shows us the path of the sun through our sky on the 4 major marker days of the year. Now, the 4 major marker days of the year are March 20th, or the spring equinox. Then we have June 21st, which is the summer solstice. Then we have the autumnal equinox, which is September 22nd, on or about September 22nd. And then we have the winter solstice, which is on or about December 21st. Now, on this diagram, the North Pole is up here on the left side of the diagram. The South Pole is down here on the lower right side of the diagram, and the Earth's equator is cutting right through the middle of the diagram here. And you can see that on March 21st, around the time of the vernal equinox, or September 21st, the sun is on the celestial equator. So let's talk about what path the sun takes through the sky on these different marker days of the year. So let's imagine today the vernal equinox. On the vernal equinox, the spring equinox, the sun rises due east. It moves across the sky, gets moderately high in the sky, and it's highest at noon. It comes down in the afternoon and it sets exactly west. On the vernal equinox, the sun rises exactly east and it sets exactly west. The other thing you'll notice about this time of the year is that the length of time that the sun is above the horizon is the same as the length of time that the sun is below the horizon. If we look at the size of the path above the horizon, you'll notice that the path length is the same as the path below the horizon here. The sun spends 12 hours above the horizon and it spends 12 hours below the horizon down there. That's where we get the word equinox comes from. It's equal night or equal day and night. That is, the length of day and night are equal. Now tomorrow, the day after the equinox, the sun will be a little bit higher in the sky, which means the sun won't rise exactly east. It'll rise a little north of east. It'll get a little bit higher than it did today. It'll set a little bit north of west. The next day it will rise a little farther northeast, a little farther northeast, and day after day it'll move further and further to the northeast. Day after day, it'll get a little bit higher in our sky until finally on the summer solstice, June 21st, the sun reaches its maximum northern extent for the year. On that day, the sun will rise in the northeast, get high up in the sky, but not straight overhead, still high in the sky though, and then it will come down and set here in the northwest. Now look at the length of that path. The sun spends much more time above the horizon than it does below the horizon. Here at the mid-northern latitudes, the sun spends almost 15 hours above the horizon and spends only about 9 hours below the horizon. The days are longer in the summer than they are at other times of the year. And this is the scientific explanation for why the days are longer. We've all known throughout our lives why the days are longer in the summer and shorter in the winter, but we often don't have a good scientific understanding for why that is. And now you know. The reason is that the sun is north of the equator. And because it is north of the equator, it rises in the northeast, it sets in the northwest, and it makes this large loop through the sky, spending much more than 12 hours in the sky and spending only about 9 hours below the horizon. And again, it's worth pointing out that on the summer solstice, the sun is not straight overhead at noon. Here at mid-northern latitudes, it's highest in the sky, but not straight overhead. Now on June 22nd, the sun will be a little bit lower, and June 23rd, 24th, 25th, the sun will get lower and lower and lower in the sky until we come to September 22nd, which is the current date of the fall or autumnal equinox. And on that day, like it did today, it will rise due east, set due west, and spend about 12 hours in the sky. And then day after day, it will get lower and lower and lower in the sky until we reach the winter solstice on December 21st. When the sun will rise far in the southeast, set far in the southwest, and just make a little arc in the sky, and most importantly, not get very high up. On the winter solstice, the sun will spend a little bit more than 9 hours in our sky, and it will spend about 15 hours underneath the ground, out of view at night. So the path of the sun changes on the 4 marker days of the year. So this diagram shows you a photograph of the sun on these marker days of the year. So the middle path here is the sun on the solstices, on the equinoxes. This middle path is the sun on the equinoxes. This upper path is the sun on the summer solstice, and this lower path is the sun on the winter solstice. And the two important things to get out of the previous diagram and this one is that the sun is up longer in the summer, and it also gets higher in the sky. The photographer who took this photograph took a picture every hour. And so if we count the number of suns that we can see how long the sun was up. So here on the equinox, we would expect that the sun should be up for 12 hours. And sure enough, if we count them, there's sunrise. The sun is up for 1 hour, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hours. If we count the number of suns here on the summer solstice, you'll see that the sun is up for about 15 hours. And if we count the number of suns down here on the winter solstice, we see that the sun is only up for about 9 hours. Now you might wonder, which one is more important in causing our seasons? Is it the length of the time that the sun is in the sky? Or is it the height that the sun makes? Because of course here in the summer, the sun is much higher up than it is in the winter time, where the sun barely clears the treetops. Well, of those two, it turns out that it's the height of the sun that makes the most difference for our seasons, and that's by far. And the example of this is that example I used with the fire a second ago. If you hold your hands out like this, you intercept much more heat from the fire. If I tilt my hands like this, I intercept much less heat. When the sun is high in the sky, a given amount of sunlight is more concentrated on the ground, that it is less spread out. Imagine that we take 1 square meter of sunlight from the sun. 1 square meter has about 1,000 watts of energy in it, every 1,000 watts of energy. And when that sunlight hits the ground, when the sun is high in the sky, it's spread over a little bit more than a square meter. But if we take that same square meter of sunlight, that same 1,000 watts in the wintertime, when it hits the surface of the earth, it is spread out over a much greater area. And in fact, that same 1,000 watts is now responsible for heating up over 2 square meters of the surface of the earth. So when the sun is high in the sky, it is more efficient at heating the earth than when it is low in the sky. And that's a perfect example of what's going on at the poles this year. Today, the vernal equinox, the sun is rising at the North Pole, and the sun will be up for 6 straight months. And you might think if the sun is going to be up for 6 straight months, there'll be no nighttime until September up at the North Pole, that it would get quite warm. But of course, we all know that the North Pole will never get as warm as it will here at the mid-northern latitudes. And that's because although the sun is up for 6 straight months, it is always low in the sky and doing a very inefficient job at heating the surface of the earth. Whereas here at the mid-northern latitudes, the sun will get quite high. And of course, at the equator, it gets almost straight overhead. It does get straight overhead on the equinoxes, and that's why the equator, with the sun always high overhead year-round, is much warmer than the poles. So thank you for joining me on this exploration of the scientific reasons that we have seasons here on the surface of the earth. I'm Ed Murphy with the Astronomy Department at the University of Virginia, and I hope that you have a very happy spring. Thank you for joining me.